Thank you. Thanks. Good morning, everyone. And I'm Ganesh, and my topic for today's talk is to learn the variability of speech from speech production. So speech production and how we can learn from speech production and apply to speech recognition to improve upon the problems that are faced in speech recognition. So that's the overall overview of the talk. So this is the outline. So I'll start with the motivation of our research and then define some objectives, and then we'll go on to a theoretical framework that we borrow from linguistics to apply to our research, and then see look at my contribution to this research. So variability in speech is something that everyone is aware of. Variability in speech occurs due to a lot of factors, ranging from the rate of speech, as in if you speak faster or slower, the way you speak changes, the sounds get transformed in a certain way, and then if you have a different accent, if you have different nativity, then there is a lot of variability in speech due to these factors. So just an example of how a simple utterance, perfect memory, changes when you speak fast is demonstrated by this audio file.
Perfect memory.
Okay, this is a clearly uttered utterance, and this is a fast spoken sentence.
Perfect memory. Perfect memory.
Okay, so the changes that that mainly occur here are in the clearly spoken speech. You clearly hear the sound T in perfect memory, and when you speak fast, you say it perfect memory, where the sound T is not produced, or it appears to have been deleted. And this is just one example of the effect of rate of speech on speech, and there are several such examples that happen every day in our conversation as we speak and change the rate of speech. This variability in speech is a big challenge for speech recognition systems, and the way currently the speech recognition systems deal with this is with contextual effects by training biphone and triphone models. So if you have 40 sounds in English, or we call them 40 phonemes, then instead of training individual phonemes for speech recognition, they train context-based phonemes, as in they contextualize the phonemes with a left context and the right context. Just an example of that is this. So if you have the English phonemes A, O, and etc. So these are the center phonemes, and you train combinations of three in the left with the left and right context. This is the way current speech recognition systems deal with variability. The immediate problem that comes to your mind when you have such a combination is that the number of possibilities is tens of thousands. So you have 40 phonemes and you have two contexts to look at, then you have like 60,000 combinations, out of which probably around 1,000 to 2,000 combinations are possible in the language. Even in that case, when you have to train models for 1,000 symbols, you need immense amount of data to cover all the sounds perfectly. So that is the biggest problem facing the speech recognition systems today. They depend a lot on the training data to be able to learn the variability. Now, to overcome this issue, we in our lab have borrowed some ideas from articulatory phonology, which is a theory from linguistics, which analyzes speech as a series of actions produced by the speech production organs. So the organs that are involved in speech production are the upper lip, the lower lip, and the tongue, the glottis, and the velum. So if you know the anatomy, you would have a better idea, but these are the organs that are involved in the production. And the theory says that speech production is a series of actions produced by these organs. And all changes that occur in speech are due to the timing effects of these actions. Okay, so this is the theory that articulatory phonology proposes. What people have, and we will come to this we will cover articulatory phonology a little bit more in detail as we go ahead. And this kind of research is not new. People have already tried to use speech production to learn speech variability and apply it to speech recognition. So there are people who initially tried to do like discrete speech production features, like every phoneme would be classified as voiced, unvoiced, or whether a stop, a vowel, or fricative, or these are called discrete articulatory features. So this was the initial attempt to use articulatory features to analyze speech. And then as data was available, absolute positions of each of these vocal tract points were collected from speech signals, and attempts were made to estimate the motion of these organs from the speech signal. And a computational framework was developed in one of the labs, and then there are people who have done work in combining speech production and acoustic features to come up with a joint representation, or you see both the worlds, the acoustic world and the articulatory world, and try to learn a common representation. And the fourth kind of work that I've come across is something that uses synthetic speech or synthetic articulatory data from speech production models and augment it to speech recognition systems. So these are some kinds of work that have been done in this area, and the objectives of my research is to use real data collected from subjects that consists of the motion of these articulators and convert it into a form that is independent of the speaker. Secondly, speech inversion. Create models that can estimate the motion of the articulators from the speech signal. Then thirdly, analyze and explain the variability in speech using speech inversion systems, and then apply these speech production features to perform enhanced speech recognition and show and prove that speech production features indeed can improve the speech recognition accuracy. So let's go a little deeper into what this articulatory phonology theory says. So articulatory phonology says that speech production can be modeled in the following way. So the real world of speech production is like this. You have the brain sending commands to the articulators on the vocal tract, which perform a set of actions, and you have speech produced as sound waves. Now there is a computational model that was developed using the phonology theory in this manner. So the commands that the brain sends to the articulators can be modeled as discrete gestural units or discrete commands to each of these articulators. So the articulators that are modeled in the phonology are the lip, the tongue tip, the tongue body, the velum, and the glottis. Now the gestural unit, there is one gestural unit for each of these articulators. Okay, these gestural units are input to a dynamical system that simulates the motion of the articulators. You get you get a trajectory that describes the movement of these articulators. So this is a computational model that models the vocal tract as a dynamical system, and the commands that are input to the vocal tract are these gestural units, and the output of the dynamical system are known as the tract variable trajectories. Now, an important distinction that articulatory phonology makes is that it models speech as a series of constrictions produced in the vocal tract. Instead of looking at the exact x and y positions of the lip, the tongue, and the glottis, they look at the relative positions. They look at the gap between the lips, the upper lip and the lower lip. They look at the gap between the tongue tip and the palate, and they look at the relative position of the tongue tip with respect to the speaker coordinates. So all these measures that are modeled in phonology are relative measures. So instead of looking at absolute measures, you look at relative measures. So this makes the features, this makes these coordinates independent of the speaker. Okay, so these whatever you want you speak in such constriction coordinates, they will be invariant of speakers. So that is the objective of representing speech in these relative coordinates. So defining tract variables. Tract variable trajectories are temporal constriction dynamics of the vocal tract. So this is a model of the vocal tract that we have shown here, and the vocal tracts are 8 in number. 2 for lips, that is the lip aperture and the lip protrusion. Okay, the lip aperture is the difference between the upper and lower lip, and protrusion is the x-axis displacement. The tongue tip has 2 tract variables, the constriction degree and the constriction location. The constriction degree is the gap between the tongue tip and the palate, and the constriction location is an angular position with respect to the speaker's jaw axis. Okay, there is an axis that is positioned at the jaw of every speaker, and with respect to that, these coordinates are defined. Similarly, there is the constriction degree and location for the tongue body, and you have constriction degrees for velum and glottis. So this is how the articulatory features are represented in phonology. This is how speech production is represented in phonology. Now this is an example of what the synthetic model generates. So as we described here, we have a computational model that inputs gestures and gives out synthetic trajectories. So this is an example of what gestures look like and what tract variables look like. So this is a speech utterance that is produced by the simulator, and gestures are basically discrete units that give commands to the lips as to close and release, and the tongue tip is, again, there are a set of commands, and once you pass these commands through the dynamical system, you get out these motion trajectories of each of these articulators. This is what the computational model does. An example of what the synthetic speech model generates is as follows. It's very synthetic and not real. It's not. That is the biggest disadvantage of the synthetic data, is that it gives you a very simplistic analysis of speech and gives you less variability. I mean, the amount of variability that you see in real speech data, like me and you speaking every day, it cannot be simulated by the speech synthesis methods. So you might get the question that your Google Maps is able to produce speech that is much better than what I showed you. A big distinction between that and this is that Google uses concatenative synthesis techniques, which cuts and pastes speech from a particular speaker and produce a speech. But this is a parametric synthesis method where you have a set of parameters and you just have to produce speech using those parameters. So you have to model the speech production in order to produce a better speech sound. So this is a very different way of speech synthesis than the Google Maps speech synthesis. Now another so that is the so the reason the problem with the synthetic speech is that it does not model real speech really accurately. So that is why in our lab we have progressed from synthetic speech data or the synthesizer to looking at natural speech data and natural databases that have collected speech along with the motion of the articulators. How do you get articulatory data from speech? So articulatory data can be collected from speakers in different methods. There are like 4 or 5 methods that exist now. So the earliest attempt to collect articulatory data was done in the 90s in Wisconsin. They used X-ray photographs to take pictures of people speaking with gold pellets embedded or stuck on different points along the vocal tract. And they collected this data and then they computed the X and Y positions of each of these points on the vocal tract and they released the database. So this is the earliest attempt. Currently there are methods called electromagnetic articulograph, where you place pellets on the vocal tract and based on the motion the electromagnetic sensor gives you the position and the velocity of each of these sensors, and you get simultaneous speech data along with motion data for each of these points. And there recently a real-time MRI method was invented and it was found to be useful for analyzing speech production, and people could collect speech data parallelly to speech production data. So these are the different methods that exist for collecting speech production data, and in our lab we usually look at data that is collected from X-ray microbeam and EMA, but not MRI. Now this is an example of what an articulatory data looks like, which was collected in the Haskins laboratory in Yale, which is one of our collaborators. So I'll just play an utterance. So this is oh my god.
The beam dropped down on the workman's head.
Just a second. Can you see it? Okay. Anyway, so this is a tool that shows you what these articulatory data looks like. The articulatory data that is collected from people contains the palate. Anyway, so it contains the palate trajectories, and it also contains the points of on different point at different points on the vocal tract. So this the red dot represents the upper lip, this is the lower lip, this is the jaw point, and this is the tongue tip. The tongue this is somewhere in the middle of the tongue, and this is at the root of the tongue, at the back of the tongue. So this is a trajectory that shows how each of these points move when speech is produced. So as you can see, this data is absolute position, absolute X and Y position of each of these articulators. The big problem with this kind of data is that it varies with the anatomy of the speech of the speaker. So like the size of the vocal tract varies with the speaker, so this data also varies with speaker. One of the tasks that we do in our lab is to convert these absolute trajectories into relative positions known as tract variables, so that we described earlier. So these x and y positions are converted into relative constriction measures using a simple geometric transformation that computes the distance between the points. Once the data has been converted into tract variables, what we do is use the data to train a speech inversion system. So this speech inversion is a method by which we can estimate the speech production tract variables from input speech signals. So the speech production is movement of articulators to speech signal. Speech inversion is speech signal back to the motion of the articulators. Now we tried different machine learning techniques for doing the speech inversion problem, and the best that worked for us is the artificial neural network. The feed-forward neural network worked the best, and the input speech had to be parameterized as acoustic features or the Mel frequency capsule coefficients, and the output to the neural network was the tract variables. Now, how well speech inversion works? So speech inversion was performed on two sets of data. One was the synthetic data that was generated by the task dynamic model, and secondly we used the actual natural X-ray microbeam data to train a speech inversion system, and we compare the performance of both these systems. So you can this table shows the correlation between the actual tract variables and the estimated tract variables. So the actual tract variables and the estimated tract variables are correlated, and these are the results. So as you can see here, the synthetic TV estimator has a much higher correlation than the natural tract variable estimator. The reason being, the variability that you see in synthetic speech is much less compared to natural speech. So we wanted to look at more variability, but when you have more variability, it's more difficult to estimate tract variables, and that is why the numbers for correlations for natural TV estimator are less. Now analyzing fast spoken speech with the tract variable estimator. So this is an example of how well the tract variable estimator performs compared to the actual data. So this is the same perfect memory utterance that I played in the beginning of the class of the lecture. So the red curve shows the actual motion of the articulators, the actual tract variables, and the blue curve shows the estimated tract variables. And this is an utterance that was not in the training data. It's from a completely different data set that we have obtained it, and this shows that it provides estimates of tract variables with reasonable correlation, only that the timing information of these of each of these constrictions are a bit off. But still, as for a performance on an unseen data point, it is definitely acceptable. That is something that we observed. Now, how does speech inversion or how does speech production impact speech recognition? So the earlier work in our lab has shown that using just synthetic tract variables, we can improve the robustness of speech recognition systems and in various kinds of noise. And we have also shown that a combination of acoustic and tract variable features improves speech recognition in small vocabulary speech. Now, we have performed several experiments using these articulatory features. The first being the consonant, estimating the consonant place of articulation. So place of articulation is the location where the tongue tip is while producing a sound. So this is for the stop consonants. The stop consonants are p, b, t, d, and k, g. So the task here is to classify p, b against t, d against k, g. That actually gives an estimate of the place of articulation. Now we in this task, what we did was we extracted the acoustic features, the MFCC features from speech, and then we also estimated tract variables from speech and combined acoustic features with articulatory features to perform place of articulation estimation. So when you do this task we obtained a 2% improvement over using just the acoustic features. So this is the final system that we had by combining MFCCs with X-ray microbeam TVs. And another experiment that we performed was doing phone classification using tract variables. This was on the so phone classification using a landmark based speech recognition system, where you identify landmarks in speech first and segment it into different segments and then perform classification on each of these segments. So the task here is to first given a speech signal, segment it into broad classes, and then for each broad class you further segment it further classify it into several classes. So the broad class segmentation is performed using a landmark toolkit that was developed in our lab earlier. The 5 landmarks are the vowels, fricatives, sonorant consonants, stops, and silence. So once the speech signal has been transcribed has been analyzed with the broad classes, each broad class segment is further classified into these subclasses. Okay, so these are the descriptions of the subclasses. The experiment, the features that were used for the classification task were the same: Mel frequency cepstral coefficients, the estimated tract variables, and the combination of MFCCs with tract variables. Now these features were not used as it is for every frame. These features were parameterized as dynamic features for every phone segment. And this is how the parameterization was done, by extracting the maximum minima and the max slope and the min slope of the tract variables from each broad class segment. Now the experiment was performed on the timid database. The training set was used for training and the test set was kept as it is for testing. And the classification was done using polynomial support vector machines that were tuned using grid search. Now the results, these are the results that we obtained for the classification task. For vowels, high versus mid versus low. The accuracy of combining MFCCs with estimated tract variables improved by around 2% over the baseline. Again, the similar results were obtained for the other broad classes, around 3% improvement over the baseline. An important observation here is that when you use just the articulatory features, the estimated tract variables, you do not see an improvement over the acoustic features. So it's only the combination of acoustic features with articulatory features that gives an improvement. Okay. Now another experiment was performed on small vocabulary speech recognition. A small vocabulary speech recognition is a task where you have a very small set of words that you have to recognize from a large set of sentences. So the utterances consist of 34 speakers with simple 6-word sequences of this form. And the total number of words are around 300, so that's not much for a speech recognition system. And the speech was combined with 6 different noise levels, and this data was obtained using from the KIME speech recognition challenge. And the approach that we took for this challenge was to combine traditional speech features, the MFCC features, with tract variables and do the speech recognition. So on comparison with the baseline, we obtained a 5% absolute improvement over the baseline on an average. So this is the final results that we submitted. So overall, when you see results on these smaller initial experiments, we see that the estimated tract variables can be used for enhancing the speech recognition accuracy for phone recognition systems and small vocabulary tasks. So the immediate next step that comes to our mind is to extend this work to large vocabulary speech recognition with acoustics and tree features estimated from natural speech. Then secondly, we also plan to use the gesture data. So we talked only about tract variables, but we have never used gesture data for speech recognition. So we also want to estimate gestures from speech signals and use gestures for recognition. And also we want to explore more new machine learning algorithms for better combination of acoustic and articulatory features for speech recognition. So in conclusion, the whole research that we perform is a combination of all these. So from linguistics we obtain the theory of articulatory phonology, and we have a lot of speech knowledge that we obtain, that people have used that to produce speech production models. They have come up with, there are lots of speech production models out there that combines these knowledge. What we bring to this research is the speech signal processing knowledge and machine learning, and we combine it with speech production data to come up with speech inversion systems, and then use these speech inversion systems to improve speech recognition systems in the end. And the hope is that in the longer run, applying speech inversion systems on a large set of data would also improve the knowledge about speech and improve speech production models. And that is also a longer time goal for the project. So overall, my thesis deals with this part of the work, and I borrow knowledge from linguistics. So these are the references. And do you have any questions? Thank you for attending the talk. Yeah.
Are there any questions for the speaker?
Okay.
So if there are no questions, then let's thank our speaker again.
Thank you.